value of an annuity. So just to connect this concept with what we talked about in the last lesson. In the last lesson, we started with a value of 0, and we made regular deposits, each deposit earning interest according to the annual interest rate, but each deposit earning, like this one earns the most interest, most compounding periods, one fewer, all the way to the end. So we're making regular deposits into an account. It's all accumulating interest, and at the end, we're going to have some value, okay? That's like, for example, looking toward retirement. You're making investments into a retirement savings account, and you want to have a certain amount by the time you get there so that you can retire well and take care of your family, etc. Okay? Today, what we're going to be looking at is, for example, the time beyond when you're retiring. You're not going to be making regular deposits anymore. Instead, you're going to start with a certain value, a certain amount in the account, and you're going to be making regular withdrawals. So you're going to be able to live off of the money that you've accumulated through that investment, and then you're going to pay yourself out of that account at regular increments, regular and constant amounts, and you're going to withdraw and withdraw and withdraw, and we're going to time it out so that the amount that we take out, by the time we've taken out every single piece, we're going to have 0 left, okay? Now, what's interesting about this is it really works the same way. Whatever you leave in the account, so let's say after compound period number 1, this amount that's still in the account is actually going to continue to earn interest. So you're earning interest on one less piece, one fewer piece each time, if that makes sense to you. It'll make more sense as we work along. It's very similar to working with annuities the way that we did yesterday. This time we're just looking at, okay, how much can I withdraw? Here's how much I have. What can my regular withdrawals be in order to end up with 0 at the end? Or if I want to be able to withdraw, $2,000 a month to live off of, how much do I have to start out with based on the interest rate of my savings account? Okay, so before we do that, we're going to dig in just with a few definitions. Okay, so this time we're going to be talking about regular withdrawals. These are withdrawals of equal value drawn at equal periods. Withdrawals of equal value drawn at equal periods. Okay, so now instead of putting more money into the account, we're going to be taking money out at regular intervals. And present value of an annuity. That's a mouthful. Yesterday, when we were saving up for something, we started with a present value of 0. Where am I at right now? I haven't invested anything yet. I'm at $0, okay? When we hear the term present value of an annuity, we're no longer talking about this situation. We're talking about this situation. How much money am I starting with before I start making my regular withdrawals, okay? So present value of an annuity is the amount of money needed, to finance a series of withdrawals. The amount of money needed to finance a series of withdrawals. That means how much money do I need to have? What's the present value in my savings account before I can safely withdraw my own regular payments to myself until a certain date or until my death, however you work that out if you're talking about the example of retirement. So how do I do that? How do I ensure that I'm going to have enough money in the account to finance all of these regular withdrawals? Well, we use the same formula that we've been using all along. Present value equals future value over 1 plus I to the power of n. Okay? And now this present value, the amount that I need to have in the account, can be determined by adding the present value of all of the withdrawals. So what does that mean? It means we're going to draw a timeline again, just like we did in the previous lessons. But in this time, we're going to be chasing our timeline backwards to now. So just give me a second to draw this out. 1, compound period 2, compound period 3, ... all the way to our which we can indicate is compound period n, n minus 1, n minus 2. And this time we're going to be making regular withdrawals. So we're going to make a regular withdrawal here, a regular withdrawal here, a regular withdrawal, regular withdrawal, regular withdrawal, and our final withdrawal. And now we can actually calculate the amount of interest that is earned on each of these pieces of money before we take it out of the account. Okay, so this amount of money, let's say I'm taking out $500 a month or $500 a week, whatever it is, okay? This amount of money is not just going to be, we need the amount that is needed in the account in order to withdraw that $500. So the amount that I need today in order to withdraw $500 in, let's say, 1 month, is actually going to be my future value, which is going to be the $1,000 that I want to be able to take out right there, over 1 plus my interest rate per compound period to the power of 1, because that money right now is only going to be in there for 1 more compounding period. Okay? Now, let's look at our next guy. He's coming over here, this regular payment, this regular withdrawal, and we're asking how much money do I need to have in the account right now in order to take out $500 or whatever this regular withdrawal is after 2 compounding periods. So I'm actually going to need less than $500 now because it's going to continue earning interest for 2 more compounding periods before I pull out the $500. We'll see this with a specific example very soon. But basically this amount, the regular withdrawal that I'm going to take out, is calculated this way. Okay? We carry this on for the 3rd regular withdrawal, the 4th, the 5th, and everything in between. And I'm just going to skip a whole bunch, come very close to the end. This regular withdrawal, this amount of money that we take out, $500, let's say, it gets compounded a whole bunch of times. So I actually need much less now than $500 in order to take out this specific $500. So this is regular withdrawal over 1 plus I to the power of n minus 1. It's going to compound n minus 1 times before I withdraw it. And for our final withdrawal, he's going to compound n times. Okay. And now in order to find out how much I actually need now, all I do is I take all of these up. The amount I need to finance my withdrawals is the sum of these amounts. All right, so here I need almost $500 in order to take out $500 in one compounding period's time. Here I need a little bit less in order to have $500 later. Here I need quite a bit less in order to have $500 later, less and less and less and less. But I need to add all these up in order to find out how much I need right now as my present value in order to finance my retirement. Okay, let's look at our investigation. In the investigation, Owen and Anna have estimated they will need to withdraw $1,000 per month for living expenses over the next 20 years. So you have their regular withdrawal of $1,000, and you have the number of withdrawal periods, okay? It's monthly for 20 years. They wonder if they're going to have enough to finance this. The amount their account earns on interest annually is 9% compounded monthly. So they're withdrawing monthly and it's compounding monthly, okay? That makes this a lot easier to do. Let's work through the questions here. Number one, how many withdrawals have they planned for? How many withdrawals are they planning for? Well, monthly is 12 times a year times 20 years. That is 240 withdrawals, okay? 2, multiply the total number of withdrawals by $1,000. Why are we doing that? Well, that's going to tell us how much money they're going to be withdrawing altogether. 240 times 1,000, I just write 240, add 3 zeros, put a comma there. So altogether, they want to withdraw $240,000 to live off of. Now, right now, they do not need $240,000 in the account right now because the money that is left in the account over time, they're pulling some of it out, but the money that's left is going to continue to earn interest, okay? Let's keep thinking through this. Number 3, do Owen and Anna need to have this much money in their life savings account? No, they don't. I just explained why. No, and there's your answer, why. 4, suppose they retire at the end of December. They will make their first withdrawal from their life savings account at the end of January. Okay, so they would be making it at the end of January, which means that that money that they're withdrawing is going to accumulate interest over one compounding period. That's just the amount that they take out in January. Okay, so that goes back to our timeline that we had before. Might draw another timeline in a second. Determine the present value of this first withdrawal, then determine the present value of the second withdrawal. Are the present values of each withdrawal equal? Okay, so you have a little bit of space there underneath 4. Let's draw a timeline to represent what's happening here. We've got now, we've got compound period 1, compound period 2. This would be January. This would be the end of February. Okay, then we're going to go 1, 2, skip a few. This is going to be, and let's just end it right here. They're doing 240 withdrawals, so we have 240 withdrawal periods. Makes this 239. Okay, this is going to be December of the 20th year, the end of December of the 20th year. And what are they wanting to withdraw? We know their regular withdrawal is going to be $1,000. They're going to withdraw $1,000 each payment period. I'm just going to put another, skip that one. And the question is, how much money do they need in order to finance each of those things? So here, they are going to need 1,000 over, and let's calculate their interest rate quickly. Interest rate is 0.09 monthly, so 0.09 divided by 12, which gives us an interest rate per compound period of 0.0075. Okay, so in the bracket here we have 1 plus that, which is 1.0075 to the power of 1. Okay, so you can see now we're dividing by a number slightly greater than 1. which means that our final answer is going to be slightly smaller than 1,000. Okay? Let's look at our next amount. We need for a present value in order to withdraw $1,000 after 2 compounding periods. It's going to be 1.0075 to the power of 2. Now look at what happens in the denominator. We are squaring a number that's greater than 1. Very slightly greater than 1, but it is greater than 1. So this number is actually going to grow. And since it's in the denominator, the overall value of this fraction is actually going to get smaller. So we will need less money to pay ourselves the second $1,000 than we did to pay ourselves the first $1,000. So the answer to 4C, are the present values of each withdrawal equal? No, these are not equal. Okay, and we could continue our chart. 1, 2, skip a few. Down here to the 239th withdrawal. Must feel good when you're getting to that point and you, well, maybe not good if you're running out of cash in your account, but must feel good to withdraw $1,039 239 times without making any deposits. But our denominator here is 1.0075 to the power of 239. It's in there for 239 compounding periods. This amount, let's just actually go ahead. Let's punch this into our calculator. And you'll see how small an amount you actually need if it's going to sit in there for 20 years before you withdraw that $1,000. And I get that this amount is only $167.66. So at their retirement, in order to withdraw this $1,000 in 20 years, they only need to have a small percentage of it really in the account, because it's going to continue to generate interest, compound interest on itself monthly at 9% per year. And that's how fast money can grow. In 20 years, it turns into $1,000 bucks. Okay, let's look at our last piece here. Bring it over. Notice how on our timeline, I'm now working backwards to the present value instead of forward to the future value. Okay. Our last piece here is 1,000 over 1.0075 to the power of 240. And if we needed to figure out the amount here, the present value, we would simply take the sum, we'd add those all up, okay? And we would get the present value of the annuity in order for our dear friends here to make this series of withdrawals and pay themselves $1,000 per month for 20 years. All right, I don't know if you have a little bit of space there or else back on the bottom of the previous note-taking page, but I'm going to write this timeline as the sum of a series, okay? So we're going to say here that the present value, which is what we're looking for, is the sum of all of these terms. And I'm just going to go ahead and write it as a series. That's 1,000 over 1.0075 to the power of 1 plus 1,000 over 1.0075 to the power of 2 plus ... ongoing plus numerator of 1,000 over 1.0075 to the power of 239 plus 1,000 over 1.0075 to the power of 240, okay? Where the first term is there, 1,000 over 1.0075 to the power of 1, and it's a geometric series with a common ratio, so with an R value of 1 over 1.0075. That means that to get from the first term to the second term, we're dividing by 1.0075, another factor, okay? To get from the second last term to the last term, we're just dividing by 1.0075 one more time. Or we're multiplying by 1 over 1.0075. Okay, that's how you talk about a common ratio. We're multiplying by this value, 1 over 1 plus the interest rate per compound period. So what does that mean? That means that we can use the formula for the sum of the first n terms of a geometric series. So we can apply the formula for the sum of the first n terms of a geometric series. And of course you have that formula memorized. It looks like this. S sub n is equal to, in the numerator, a bracket r to the power of n minus 1, close bracket, over r minus 1. We can talk about this in terms of our present value, future value, annuity language. Okay, just gonna give us a big arrow here. The present value of an annuity then can be determined by simply substituting the things that we know about A and about R, okay? This is a specific case. I'm gonna sub it in the values for the formula using a general case. So we have present value is equal to our regular withdrawals, square bracket, 1 minus 1 plus I in brackets to the power of negative n, close square bracket, all over I, where R is the regular withdrawals, I is the interest rate per compound period, and n is the number of compounding periods. All right, let's go. Example 1, present value of an annuity. Josh is putting his summer earnings into an annuity from which he can withdraw living expenses while he's at university. Way to go, Josh. He will need to withdraw $900 per month for 8 months. Interest is earned at a rate of 6% compounded monthly. Draw a timeline to represent this annuity. So let's record what we know. Known info. We have a regular withdrawal of $900. We have monthly for 8 months, so n is 8. We have an interest rate of 0.06, that's 6% as a decimal, for monthly, which reduces to 0.005. All right. Timeline. Now, right. Compound period 1, compound period 2. These are the months that Josh is in school for, after the first month, after the second month. Okay? Skip a few. 7th month, 8th month, and he's done. He wants to withdraw $900 per month. Great. Now to calculate how much he needs, let's switch colors because switching colors is fun. The difference between blue and purple is pretty negligible in the camera, but I can see it. How much does he need in the account now, saved up, in order to pay himself $900 in 1 month after another compounding period? Well, he needs R, which is 900, over 1 plus I, which is 1.005, to the power of 1. What about after 2 compounding periods? He needs his withdrawal, 900 over 1.005 to the power of 2. Oh, great. What about after in his 7th month of university? 900 over 1.005 to the power of 7. And the last month, 900 over 1.0075 to the power of 8. Wonderful. B, how much does Josh need to invest at the beginning of the school year to finance the annuity? We're just taking the sum of these. So you could add these all up in that long equation of a series, or we could just take the information that we know, plug it into our present value formula, B, which looks like this. PV equals numerator R square bracket 1 minus bracket R1 plus I, right, to the power of negative N, not M, close bracket, denominator I, sub in what we know. What do we know? We know R is 900. 1 minus 1 plus I is 1.005 to the power of negative N, which is negative 8. Close that off. Go up here, down here, 0.005. Carefully punch that into a calculator. You can reduce this part first, but when you do that, please, oh please, make sure that you're following the rules of math. BEDMAS. Okay, so you need to do 1.005 to the power of negative 8. Then do 1 minus that amount. Okay, then multiply by 900. Then divide by 0.005. And you should end up with approximately $7,040.66. So this is how much Josh needs to have in his account in order to finance his 8 months at university. Now, how much is he actually withdrawing? Well, 8 months, $900, $7,200. So his investment's going to continue to earn while he's in university withdrawing it, and it's going to earn an extra $160 for him, okay? Now, what would be really interesting is to calculate, okay, so he needs $7,040-ish in order to finance his stay at university and his living expenses. So let's continue working backwards and say, what are the regular payments that Josh would need to make into this same account at 6% interest per year in order to finance his 8 months at university? And that's when we start getting real practical application in a lot of ways when we're talking about saving and withdrawing money. So there we go. Josh needs to invest $7,040.66 in order to pay for his living expenses at his first 8 months of university. And that's convenient because that's probably about how much you can make in a summer working. So next summer he can save up for the next 8 months. Example 2, determine the regular withdrawal that Fiona can make based on the amount of money that she has saved up. So Fiona's life savings totals $300,000 when she decides to retire. She plans an annuity that will pay her quarterly for the next 30 years. If her account earns 5.2% annual interest compounded quarterly, again, thank you book that the compounding periods is the same as the withdrawal periods, how much can Fiona withdraw each quarter? Again, we're going to be using the same formula, same strategy. We just need to gain some information. So let's look at our number of compounding periods. She's got 30 years, and we're looking at quarterly. That's an end value of 120. Let's look at our interest rate. She's earning 5.2%. That's 0.052 annually, and she's going to be compounding this thing quarterly. So we're going to divide that by 4, and we get a interest rate per compounding period of 0.013 as recorded as a decimal. And we know the present value. She has $300,000 saved up. So we're just going to use the formula for the present value of an annuity in order to solve for the regular withdrawal R. So PV equals numerator R bracket square bracket 1 minus little bracket 1 plus R to the power of negative n, close that bracket, all over I. Subbing in the values that we know. We know her present value, 300,000. We do not know R. We know the interest rate, R. I put in the wrong letter here. This is not 1 plus R in the formula. It's 1 plus I. Interest rate per compounding period, not interest rate per year. Good. So we have 1 plus 0.013. That is 1.013 to the power of negative n, which is negative 120. Close it off. All over I, which is 0.013. All right, algebra, what are we going to do? We are going to multiply both sides by 0.013. So 300,000 times 0.013 is 3,900. And on the right-hand side, we're left with just the numerator, R times 1 minus 1.013 to the power of negative 120. Step 2, we're going to divide both sides by this awkward bracket, 1 minus 1.013 to the power of negative 120, which leaves us on the right side, swapping sides, with just R. And on the left side, we have 3,900 over that messy bracket. And in order to do that, you're going to be very careful on your calculator. You will get a regular withdrawal of $4,950.87. So Fiona can withdraw almost $5,000 every quarter, that's every 3 months, for the next 30 years. If she decides that, oh, whoa, that's not as much as I expected it to be, one of her options is simply, okay, I'll work another half year, or I'll work another whole year. And what that would do is she would, A, continue to earn, so this value would go up, okay? And this value would stay the same, but the number of withdrawals that she's going to make is going to also go down, okay? So she's going to need money fewer times. She's going to have more money to start with. She's going to do it for a shorter period of time because she's going to take a whole year off her borrowing. She's going to work for another year instead. So she's taking off 4 payments and adding all of her income to the investment. Now all of a sudden, she can withdraw $5,500 over the course of her retirement. So there's different usefulnesses. There's different uses for this and figuring and calculating and very practical financial math here. So that's the end of lesson 7.5, present value of an annuity. Your practice problems are found on page 461, numbers 1 through 11 and 13. Thanks for joining me today.